Welcome back to Arxflix. Today, we're examining the fascinating research paper titled An Explicitly Relational Neural Network Architecture, written by Murray Shanahan, Kyriakos Nikiforou, Antonia Cresswell, Christos Kaplanis, David Barrett, and Marta Garnello. This paper aims to bridge the gap between deep learning and symbolic AI by introducing a novel neural network architecture called PrediNet. Here's an overview of the PrediNet architecture. The core innovation here is that PrediNet learns to form propositional representations with an explicitly relational structure from raw pixel data. Let's jump into the main components of this architecture. Humans excel at reusing past experiences to solve new, structurally similar problems. This ability is essential for lifelong, continual learning. How can we develop systems that emulate this ability? The key is to construct general-purpose, reusable representations. Currently, many deep learning systems lack this capability. Representations they generate are often task-specific and hard to interpret or reuse. The goal is to build a system that can form reusable representations and use them to accelerate learning on new tasks. This would make machine learning more data-efficient and robust. PrediNet aims to emulate the capabilities of classical symbolic AI while retaining the benefit of learning from data. It builds propositional, relational priors into the neural network, similarly to how convolutional networks use spatial and locality priors. PrediNet focuses on discovering and utilizing relational information. The PrediNet module works in 3 stages: attention, binding, and evaluation. It selects pairs of objects, binds them to relations, and evaluates these relations. This process ensures that the final representations are explicitly propositional and relational. PrediNet's attention mechanism uses key-query matching to select pairs of objects. Each head in the PrediNet computes a pair of queries from the input data and matches them against a shared key space, generating a set of relational propositions. These equations show how queries Q and H and QH and the key space K are derived from the input matrix L. The evaluation stage in PrediNet computes the values for each predicate's argument to make the proposition true. It uses vector differences between object feature vectors to compute these values. Lastly, the outputs from different heads are combined to form a final relational representation. This final output vector, R, can then be used for downstream processing tasks, providing a structured, interpretable representation. To evaluate PrediNet, the authors introduced a new family of tasks called the relations game. These tasks are simple visual reasoning tasks designed to test relational reasoning. Here's a snapshot of the relations game setup. The aim is to label images as true or false based on relationships between objects. This setup allows us to test how well the architecture learns representations that are general purpose and reusable. The results are remarkable. PrediNet significantly outperforms several baseline architectures in tasks requiring relational reasoning. This figure shows how PrediNet performs in a multitask setting compared to baselines. PrediNet not only learns faster, but also achieves higher final accuracy, demonstrating its ability to form reusable representations that facilitate transfer learning. Another exciting aspect of PrediNet is its interpretable attention masks. This figure shows how the attention heads focus on relevant parts of the image. Most attention is directed at the centers of objects or meaningful pairs of objects. PrediNet marks a significant step towards bridging the gap between deep learning and symbolic AI. Its explicitly relational structure facilitates data efficiency, generalization, and transfer learning. Future research could explore more complex tasks and integrate PrediNet with other neural modules for advanced reasoning capabilities. You can find the full paper and supplementary materials on http://r5ive.labs archive.org HTML 1905.10307. Be sure to check it out for more in-depth analysis and experimental details. Subscribe to Arxflix for more exciting deep dives into cutting-edge research. Until next time. Thanks for watching Arxflix. where we bring you the latest in AI research in an easy-to-digest format. If you enjoyed this video, don't forget to like, share, and subscribe. See you in the next one. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.